Okay, our next speaker, Hugo Landau, is specialized in reverse engineering and a strong proponent of open firmware, open software, and the right to own your hardware. Open stage for his talk entitled Adventures in Reverse Engineering Broadcom NIC Firmware.
Thank you. Hi everyone, and welcome to my talk, Adventures in Reverse Engineering Broadcom NIC Firmware. So this is a story about how I ended up reverse engineering the firmware to a Broadcom Ethernet controller and why I was motivated to do that. So in order to understand why I did this crazy thing, I actually have to take you back to when I was 10 years old. I was into computing, just as much as I am now, and I heard that the soon-to-be released Windows XP, this was in 2000, would have this feature called product activation. And this is a DRM feature, right, where they think you might be trying to pirate Windows, so they prevent Windows from working until you literally get authorization from the Windows Microsoft mothership, and until then Windows will refuse to work. And I was only 10 years old, and I had never heard of the FSF or open source. I had never even used the internet, but I intuitively knew that this was fundamentally wrong and boycotted Windows XP as a 10-year-old. So why did I do this? Because I intuitively knew that your computer should be on your side and not anyone else's. And that is something I believe to this day, and that's something I fight for to this day. Your computer should be on your side, but is it? No. Product activation, DRM, locked bootloaders, typerization. Your smartphone is controlled by Apple or Google or whoever, whenever or not you want it, even if you don't want it to be. These are all things that we'd call anti-features, right? It's a term someone invented for features that were designed to benefit the manufacturer's interests over yours. And it goes beyond just computers now. Anything with a chip might be used to try and control you, because companies have figured out that they can use software to control how a product is used after they sell it. You know, it depends on the country you're in, but there's this legal principle called the first sale principle, which is basically a law that says, after someone sells something to you, you can do what you like with it. They don't have a right to tell you no. But companies have figured out that it doesn't matter what the law says, they can use software to work around that and effectively impose their control on you on this product they've supposedly sold to you after they've sold it to you. You know, printers print cartridges, they try and prevent you from using third-party print cartridges. CNC machines that literally have a GPS chip in them and will shut down if you move them. That's a real example. Cars, where if you try and hook into an Ethernet port you discover under the bonnet, the company that made the car literally calls you up and tells you off. Tractors that you can't repair. And being given as a talk today, even trains. I highly encourage you to attend that talk being given today about DRM in Polish trains at 11 p.m. And these are all real examples, right? And the best citation I can give you for this is The Coming War on General Purpose Computation by Cory Doctorow, who really sounded the bell on the start of this battle. So the basic principle that we have here is one of owner control. And in my view, a simple principle must be defended. All hardware and software must be designed to put the interests of its owner first, over any vendor, any third party, and any government. And that's what I believe. And in a way, if you want to think about it like this, owner control is like the diametrical opposite of DRM, their matter and antimatter. So how do we make this a reality? So you can make free software for your operating system, you can make free operating systems, but at some point, the rabbit hole starts going really deep, and you find anti-features in firmware itself, where the people that made the hardware have put that there. So I would argue that if we are to have owner-controlled machines where we can know that what we're using is on our side, all of the software and firmware on your machine needs to be yours to audit, inspect, and change to your needs. All of the firmware on your machine, I would argue, therefore, must be open source. It really goes back to Richard Stallman at the very beginning, getting annoyed because he couldn't fix a bug in a printer driver. And what's interesting is that if you have open source firmware on your machine, anti-features are sort of impossible. I mean, if you don't like a feature, you can just remove it. The ability to impose anti-features is one motivation a company has to keep a feature proprietary. So if a company says, we don't want to open up this firmware because then you, the user, could remove this feature that we put in there, I would argue that by definition, if a vendor is saying that, that feature is an anti-feature. Think about it like this. Open source DRM is an inherently nonsensical concept. It can't be. And it's not just about owner control. It's not just about the ethics side of it. It's also about security. We need to be able to audit firmware in order to trust it. How do you know that there isn't a backdoor? But often it could just be a 0-day in shoddy vendor code. And the quality of a lot of vendor firmware is often astonishingly low. I have myself personally managed to brick a laptop by installing Linux on it. As in brick, as in not, it won't boot, as in I can't even get into the BIOS menu. Because companies, they just want to get things working. They ship firmware as soon as possible. They never patch it. And often when people and security researchers go in there and actually look at how things work, they find that actually it's full of holes. And of course, there's an increasing concern about supply chain attacks. And every company shipping proprietary solutions seems to be saying, well, we're just going to make it so the firmware has to be signed by us, and therefore it's safe. And I'm sorry, but that is a terrible security model, and it's one that's fundamentally antithetical to owner control. That, by definition, is vendor control. But you also have things like reproducible builds, and a lot of people have done a lot of work over the past few years to enable reproducible builds. And you need open source in order to be able to do reproducible builds. I don't know how many people here have read the famous paper Reflections on Trusting Trust, where it turns out actually you can't even trust your compiler, even when it's compiling another compiler. And with reproducible builds, you can actually start to mitigate some of those concerns. But with x86, we have hit a dead end. Both Intel and AMD have these signed firmware blobs now which can't be replaced. The hardware will only boot code signed by them. You may have heard about the Intel Management Engine or the AMD PSP, which is the exact same thing, basically. They've built investments on making sure that you can't control these processes that are hidden on your x86 system. They use these for DRM and so on and other functions. They've invested in making sure that you don't have full control over your machine. And they have gone so far down this road now that honestly I think they're never going to come back from it. So it seems like x86 has become a dead end. And of course, you have many small single-board computers that are fully open firmware, but they're not fast. So there's this question here, where can we get a desktop or server with open firmware? And it actually looked pretty bleak for a while until it turns out IBM all this time, all these years, has been making very expensive servers with their own custom CPUs, power CPUs. And amazingly, a company in Illinois wrote to them and said, would you open up all your firmware? And to my astonishment, they said yes. So the result of this is we got this computer known as the Talos 2. It's an E8X motherboard. You can literally build it yourself like any other PC, but it's not x86, it's Power 9, and it has 99% open firmware. But why is it only 99%? Well, it's because there's this Broadcom Ethernet controller that has a firmware blob. So let's reverse the firmware and get rid of it. And that's how I ended up reverse engineering this chip. So the BCM5719 is an Ethernet controller. On one side, you have PCI Express. You can get it as an add-in card you plug in your system. And on the one side, you have 4 Ethernet ports, up to 4 Ethernet ports. It's the 13th generation of an incredibly long line of chips that actually descends all the way from the Tygon NIC, which was released by Alcyon Networks in 1997. And they haven't really changed a lot of this hardware since then. They've just been tinkering around the edges. And it is literally a direct descent from this chip to do gigabit Ethernet that someone released in 1997. And somehow the IP ended up with Broadcom at some point. So this chip, the 5719, is particularly oriented to server applications. And it has management-style functionality. So there is something called NCSI, which is basically something that allows the server's BMC to share the host's network connection and piggyback on the host's Ethernet ports. So if you're not familiar, modern servers have what is called a baseboard management controller. And it's basically an SoC implementing management features like IPMI, serial over LAN, etc. Any modern server has this. And yes, it usually runs Linux. This BMC has a network connection, so you can communicate with it. And using a whole separate port on your machine to access the BMC might be wasteful. So NCSI is this protocol which allows the BMC to be attached to the network interface controller of the host and actually share its network connection and piggyback on the same Ethernet ports. If you've ever used a server where you can just plug into any old Ethernet port and get it via IPMI, this is NCSI. So the basic block diagram of the 5719 is that we have 4 Ethernet ports, and we have 4 PCI functions on the other side. And the PCI function is basically a separate device. So to the host, this looks like 4 different devices. We also have a flash interface where it can load some mysterious firmware from an SPI flash chip. And what's interesting is that in the middle here, between each port and each PCI function, these are then connected together, but they also have a MIP CPU in the middle. So for each port, we have this MIP CPU running some kind of unspecified firmware where there's kind of a question of what's going on here. But as mentioned, this is a server chip, so it's also intended to have this management link where you can connect to BMC. And basically, that's a parallel Ethernet interface which attaches into the Ethernet chip, and it can actually piggyback on all of these ports. So you've got traffic coming from both the BMC and the host. And then, this is on Broadcom's block diagram. There is this mysterious thing called the ape, and it takes some kind of firmware image, but it's not clear what it does. Presumably, it is some kind of CPU, but I didn't know. It was just this completely mysterious black box that nobody seemed to know anything about. So I started by examining the flash image layout. I just took a dump of the SPI flash, and I looked at what was in there, and I pretty quickly figured out it's not hard to figure out the things that they've got sitting in that flash. You've got a header that points to the various images. You've got MAC addresses, configuration, that sort of thing. Then you've got this firmware that gets loaded onto those MIPS cores you just saw. So that's running per port. And then you've got things like option ROMs. So this is actually a code image that is actually fed to the host when you boot. And that tells the host how to do things like PXE boot. And because this is oriented for servers, it actually supports also ISCSI boot. What's interesting here is that we don't actually care about most of this. I mean, the Power 9 system I'm trying to free up here doesn't even use PXE option ROMs, which is great because they're not really great from a security perspective. So the only actual code here that needs to be reversed is this MIPS firmware and this mysterious ape firmware. So I looked into the MIPS. I started reversing this firmware. It turns out each port has a truly ancient MIPS core. It's roughly MIPS 3. There's no hardware multiply or divide. The multiply and divide instructions don't exist. I fully reversed engineered the firmware for this, but it turns out that these cores are almost vestigial. I mean, it is amazing how little they do that's actually important. They do some things. They do things like they load the MAC addresses from flash into the right registers, and they do a lot of register setup for the Ethernet filings. But that's about all. And these cores are actually left nowadays with almost nothing to do. In the original days of the Tygon, back in 1997, I believe that these cores were actually handling data paths, so they were actually spooning data from the network and back. But that's all since been moved into hardware, and these cores are left with almost nothing to do, but a few very miscellaneous things. So what do they still do? They load MAC addresses. They set up file registers, but even a lot of this code turns out not to be enabled in practice, and it's just vestigial. And after it does all that initialization, it enters an infinite loop checking if certain housekeeping tasks need to be performed. What housekeeping tasks? Well, namely this. So let me take you through this. This is from my reversed code. I converted all the assembly into C. So you can see these first two function calls here. They don't actually really do anything, basically 99% of the time. You have an infinite loop, and then you have a check to see if we're on vmain, which means if we're on the main power rail where the host is on, and if the host is off, it's on standby power, and that's called vox. And then we just call this function, and then we loop again. So we're just calling this function again and again and again if the host is on. So what does this function do? This function implements a PCI Express capability. This is a standard in PCI Express that lets you see if you are querying the host is querying for the device's serial number. I am not making this up. If you have a BCM5719, after the machine is on, the device spends all its time for each port checking if you are querying for its serial number, and that's 4 MIPS CPUs, one for each port, and each of those independently checks if you're querying that specific port for its serial number. These cores implement random dregs of functionality that nobody has bothered to move elsewhere. I mean, if you're a Broadcom engineer, do you really want to be the person tasked with moving VPD loads into hardware? Probably not. Your princess is in another castle. So these MIPS cores do some device initialization, but they are otherwise largely unused. And there is this mysterious ape block on the device. So is it a core? Is it something else? Broadcom doesn't say. There is this ape code image on the flash. There are some references to NCSI in the code. So presumably, there is some core which implements NCSI. So I needed to reverse engineer this code. But the image is compressed with an unknown algorithm. And the memory for this ape CPU doesn't seem to be mapped in from PCI Express or from the MIPS cores. So you can't actually access its memory directly. So how do we get into this thing? And this brings me to the story of how I ended up reverse engineering x86 real mode decompression code. Problem 1. I want to disassemble the ape code, but the ape code is compressed. And I can't recognize the compression algorithm. It doesn't seem to be a common one, but it is a really bad one. Problem 2. I want to gain access to the ape memory space, but it's not mapped into PCI Express or accessible indirectly. You can only access it from the ape core. And the only way to gain execution on the ape core is by providing a valid firmware image. So this is a conundrum. I want access to the ape address space, but it is not mapped into the PCI Express space. The only way to get access to its address space is to provide a well-formed firmware image. Formulating such an image would require me to understand the compression algorithm, which would require me to dump the ape boot ROM, which would require me to gain access to the ape's address space, which would require me to gain execution on the ape, which would require me to provide a well-formed firmware image. It's a circular dependency. So the problem is decompression. We need to decompress this ape image in order to study it, but we don't have the decompression code. The boot ROM for the ape must have it, but we can't seem to find any way into the ape's memory space, so we have a circular dependency. So at this point, I decided to take a break and look somewhere completely different. The SPI flash also contains things like PCI option ROM images, which I thought were of no interest. And they actually look as though they're compressed with a suspiciously similar algorithm. And since they're option ROMs, they must be self-decompressing. So they must contain the decompression code. So there's 2 PXE images. There's the legacy PC BIOS mode, which runs in real mode. This is like the original PC BIOS. And there's the UEFI BIOS, which is modern protected mode code. And obviously, I'd rather reverse the latter. But it turns out that the UEFI images are compressed over their own special algorithm, which is in the standard. So it's compressed with a different compression algorithm. So the decompression code I was looking for is only really found in the x86 real mode image. Oh no, I said. So I had to reverse engineer this x86 real mode code, which, to put it shortly, is not fun. There's no decompilers for it. You can forget that. So with x86 real mode, because it's in 16-bit addresses, you actually need segment registers to address more than 16 bits. And those segment registers are constantly being changed and make everything confusing to follow. So if you have a simple load, for example, you can load from BX, which contains a memory address, into the register AL, but it's relative to the segment register ES. And the compiler that Broadcom used to generate this code constantly changes the value of ES as needed, so it makes following the code extremely confusing. Imagine debugging like a normal program for protected mode if the memory mappings kept changing, and that's pretty much what you're dealing with. So I tried to reverse engineer this in an ad hoc way, but that didn't really work. The code I ended up with had bugs, and that led to changes in the decompressed code where it silently corrupted some of the code that I was trying to disassemble, which explained a lot of baffling disassembler output. So I realized I needed a way of reversing this code which cannot introduce bugs, because otherwise I would just go on a wild goose chase where I'd spend days trying to figure out why this disassembly doesn't make any sense, and then I realized that's not disassembly, you've decompressed this image wrong, it's corrupted output. So then I came up with this idea to have a methodical approach that can't introduce bugs. And this was where I had the idea that I should construct an x86 real mode emulator in C. Emulator is too big a word. Every line of x86 real mode assembly was turned into a C comment, like this. And I then constructed an emulation environment for real mode code in C. I say emulation, and what I actually mean is, it's just a global variable. I have a global variable, which is the current value of the ES segment selector in x86 real mode, and I have global variables for each of the x86 general registers. And then I just have a function which sets ES, and then I just have a function which does an ES relative load. And then beneath each line of assembly, I then placed an equivalent line of C beneath it. So you just have it, it's perfectly simple like this. We have a move to the ES segment selector, so we're setting ES, and it just translates to this line in C targeting my emulator. We have a move from one general register to another, and that's literally just an assignment of this global variable. We have an increment operation, and then we have an ES relative load, where it's saying, load into AL from this memory address BX, which is relative to the current value of the ES segment selector. So every single line of assembly just translates into some really simple line of C. And the idea is that every conversion from assembly to C, every line has a trivial and obviously correct translation into this x86C dialect below it. And the great thing is you can keep eyeballing this to check if the correspondence is correct. If something is wrong and it doesn't match up, it stands out immediately. There's no structured control flow here. It was all go-tos, no loops. And this successfully compiled as a Linux binary, executes, and it fully decompressed the 8 firmware for the first time. So at that time, I was left with this really awful C code, and I actually wanted to understand the algorithm. So I recorded the output of this decompression program, and I then modified it to raise it into more readable C. So I converted go-tos into if, for, while, etc. And after the smallest change, I would just rerun it and see if the output had changed. So any mistakes in doing that raising process to get it into actually readable C were immediately caught, and those did happen. And eventually, with this methodical approach, I actually got a completely readable, clean C description of that decompression algorithm. So I already had the firmware decompressed at this point, but interesting point, I was actually able to determine the nature of the decompression algorithm. It's really simple dictionary compression. The only state is a 2K byte dictionary buffer. You just have literal values, and then you have references to this dictionary buffer. I was able to determine the identity of the compression algorithm. It is called LZSS, and it has a Wikipedia article. It has a very interesting statement on it. Most implementations stem from a public domain 1989 code by Haruhiko Okumura. There's a little citation link at the end there. Simtel.net Mirror, implementation of 1989. The decompression code was linked from Wikipedia the entire time. It was posted to a BBS in 1989, and it's public domain code. The decompression code fits on one screen. It is actually a really simple algorithm. The The Broadcom version does change some constants a bit, but it's basically the same algorithm. Your Broadcom option ROM for your network interface controller is compressed using some DOS compression code someone posted to a BBS in 1989. If I had known the code was lying on an Internet Archive of 1989 BBS postings of all places the entire time, I could have saved a lot of pain. The only thing better than reverse engineering real code is finding out you didn't have to. But I couldn't have figured out which algorithm it was without going through that process, especially since they changed some of the constants. So once again, it's locked doors and circular dependencies. It's a bit like Alice in Wonderland. So finally, I get this code decompressed. So how do I penetrate the ape and actually break into this inscrutable black box? I start disassembling the code now I've got it decompressed. And it actually turns out to be an ARM Cortex-M3. And this was actually the first time I actually knew what CPU it was. I had no idea what it was until this point, where I finally found out it's just a Cortex-M3. It's a common 32-bit microcontroller, like something you'd get on an STM32, that sort of thing. And the ape has I/O peripherals and registers that are not mapped into PCIe. These are completely reserved to the ape and special. I want to get access to these. So, because I know how to decompress this image, now I could write a tool to build an image and flash it, but the image headers were still a bit mysterious to me, and I wanted a quick way in that didn't require me to flash an image to the SPI flash permanently. I wanted to be able to boot from RAM, because that's obviously more convenient for development purposes. And at this point, I suddenly discover that the ape firmware image appears to have an RSA signature at the end. Oh no, is my reaction. Oh no, 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 no. I suddenly get very depressed. I only really continued at this point after some encouragement from others that really made it clear to me how much people value this work. I honestly have them to thank for this. People told me, maybe they aren't checking the signature. Maybe they just completely ignore this signature that they put there for some reason. I'm skeptical. Have I mentioned that reverse engineering is an emotional roller coaster? More on this later. So I looked for ways to get shellcode execution on the ape using the existing code. There's lots of shared memory for communicating with the host. There's like this IPC mechanism based around shared memory with a mailbox-style mechanism, where there's this SRAM shared with the host and the ape that is used to send commands to the ape. One of these commands allowed scratchpad read and scratchpad write. Well, that sounds interesting. Turns out it lets you read and write from any area, well, not any area in the ape's RAM, because it's bounds checked. Except that their bounds checks include an area of the ape's code. What? So all I had to do is send scratchpad write commands to upload shellcode to a certain code region that is within the bounds that are checked. And I send a command which happens to cause the ape to jump into that code region, and I have shellcode execution. If anyone is wondering, I wouldn't really consider this a vulnerability, because you can only do this from the host. And the host is trusted anyway. The host can actually reflash the firmware on the SPI flash anyway, so all this does is save you writing a new image to flash, so it's useful for debugging. And if anyone's curious, I didn't find any remotely exploitable vulnerabilities in the code during this entire project. So I then wrote some shellcode for the ape. I implemented a shared memory mailbox IPC mechanism, which is very similar to that used by the ape firmware itself, and it just allows me to arbitrarily load any memory address, store any memory address, or jump to any address I like. I also added a hard fault handler to this, so if you try and load from a memory address that doesn't exist on this ape, the CPU will crash. So I added a hard fault handler so that if I try and access some area of memory that doesn't exist, I just get an error back and my shellcode doesn't crash. And this means I can now access all of the ape's private memory space, which is great. It was the first time I actually got to look at the ape's own memory space. And because of this, I was finally able to dump the ape boot ROM. This was the first time I'd ever managed to get access to it. As a result of this, I got a much nicer ARM copy of the decompression code. If only I'd found a way to get to this copy first. But again, circular dependencies. At this point, I was able to determine the image header format, and it turns out that the boot ROM actually has a way to boot an ape image from SRAM instead of flash, which is also quite useful. Also, the ape boot ROM does not check the RSA signature on the ape code image. Why is it here? Just goes to tell you, sometimes they add a signature for no reason. At this point, I knew how to get execution on the ape and form valid firmware images, so I just started writing a lot of tooling. I wrote build tooling that allows building these custom image format in C. So I could just write code in C and it would be built to this custom image format. I needed the compression function as well as the decompression code I'd already obtained through that excruciating process, so I just used the original BBS code for the decompression code. I also wrote debug tooling so that I could probe the ape registers using my shellcode, boot images from memory, etc. So I comprehensively reverse engineered the ape code and I developed an understanding of the ape's special peripherals. The registers were completely unknown. There was no documentation for this. Broadcom publishes a register manual for the PCIe registers so that you can write drivers for the device. So that was a big help when I was looking at the MIP side of things. But for this ape, everything was completely undocumented. Broadcom does have a diagnostic tool which did provide some information on some registers, which was lucky. Basically, it had code to read some registers and print diagnostic output where you had textual output saying this bit is set. So that managed to serve as a kind of Rosetta Stone telling me what registers did what and what the names of different registers were. But others simply had to be guessed. So the ape has a few special peripherals. It's got a peripheral to talk to the BMC with this RMI interface. So this is a standard interface between an Ethernet MAC and a PHY. It's a parallel interface. And usually that talks between an Ethernet MAC and a PHY, but for NCSI, it's also used to actually connect the BMC to the network controller so it can piggyback on that network connection and access the internet. It also has a peripheral to talk to each network port. So it has one to transmit to each network port and one to receive from each network port. But you actually don't want this ape to receive all the traffic from the network because it's just a Cortex-M3. It is not powerful. So the ape does not receive everything from the network. You have some management filters, which are also implemented in hardware, which configure what actually gets redirected to the ape from the network. There are also SM bus and UART peripherals on this chip. They are not really wired up or used on the Telos Power 9 systems, so I did not investigate them. They are mainly for quite boring management functionality, which isn't really of interest to us. And of course, the ape can also access the rest of the chip, really. It can access all of the main device registers. So previously, I showed you this block diagram where we have this mysterious ape. And this is what it actually looks like. You can see we've got this Cortex-M3 CPU. We've got this MAC, which allows us to connect to a BMC, and that's a peripheral attached to the ape. We have these SM bus and UART things which aren't of much interest to us. We have these network transmission and reception devices which allow us to communicate with each network port. And this allows us to piggyback on each network port. And for the reception side, this is all controlled by some RX filters. So what does the ape actually do? We know the purpose of the ape is to let us attach a BMC to our network controller and share the network connection. What the ape basically spends all of its time doing is it just reads Ethernet frames from the peripheral that connects it to the BMC. It is a really simple FIFO interface. It's literally just one register, and each time you read the register, you just get 32 bits of an Ethernet frame. So it's a really simple UART-style FIFO interface. It's basically mem copying out of a FIFO. So the performance of this isn't great. You're never going to get gigabit out of this NCSI link. So basically, all the ape does is it just reads mem copies frames out of this FIFO, and then it writes it to a specific port-specific SRAM, which is basically the actual memory of the port itself. It's actually write-only memory. So it goes directly into the a memory-mapped area, which maps to the actual network port. And then you set some registers to get it sent out. And on the reception side, it's the exact same thing in reverse. There's a special region of read-only port memory, which just gives you access to the frames as they come in. You get an interrupt, and you copy them into this little FIFO, and they get sent out of the BMC. And the ape basically just does this over and over again. So it's basically a CPU just doing mem copies of Ethernet frames from one device to another and back and forth. So if the ape were malicious, if its firmware to get compromised, what could it do? Well, we can set management filters to do matches on packet headers to determine if they get forwarded to the ape. Now, for simple unicast traffic, the ape can actually set a MAC address that says anything for this MAC address just come to me. But there's some traffic that doesn't match up with that is broadcast and multicast, and that needs to be an exception, and that's what the management filters are for. So the ape sets up some management filters that says if there's a certain field in the IP header or UDP header or so on, direct this to the ape. And this is used to direct things like broadcasts, multicasts, DHCP, ARP, IP version 6 neighbor discovery, that sort of thing. These management filters actually let you choose. It lets the ape choose whether the host also gets a copy or whether the selected traffic only goes to the ape. So the ape can eavesdrop on traffic from the network. It can send traffic to the network. It can prevent the host from seeing traffic from the network. And it can man in the middle traffic between the network and the BMC. And that's actually quite alarming if you think about it for a moment, because how many servers with BMCs come with default passwords? If your BMC is compromised, if your network controller is compromised, well, it can just log into your server with a default password and then it owns the box. But, vendors are getting better nowadays. They're starting to stop shipping servers with default passwords. But even if the box doesn't have a default password, it could just man in the middle SSH. Now, you can check the SSH host key, but how many server vendors do you know ship the SSH host keys for your BMC with the machine? And how many people, when they're connecting to a BMC of a server for the first time via a network connection that is literally coming out of your laptop and going into a server right in front of you, how many people are going to shake that SSH host key, if they even can? So in practice, yeah, if you get a server, if you buy a server and the ape on it has been compromised, it could own the box. So this is quite interesting. Finally, I'd just like to leave you with some of the most ridiculous skeletons that I found in all of this firmware. There's various things that were discovered in this firmware that are just nuts. But the worst one of all is something that I like to call the Great Broadcom bitbang. You will not believe what it is. We were able to build our own replacement firmware for the ape and get NCSI working. We had working NCSI with open firmware, but it only worked after the machine had been turned on once. So part of the point of NCSI is you can access the BMC when the machine is off. And if you turned the machine on and then we turned it off again, you could do that. But if you literally unplugged it and plugged it back in, you wouldn't be able to talk to the BMC until you turned it off and on again. So the implication is that there's some kind of device initialization that was being done when the machine was turned on that we were missing. And once you turned the machine on from cold, when you plugged it in for the first time, that initialization hadn't been done, so you couldn't actually talk to it. This code was found in the reverse state firmware, and it was pretty weird. Now, let me just simplify this for you by converting it into pseudocode. So this is what this code is doing. It's reading the chip ID register, and it's only doing things if that chip ID register reads 0. Well, that's really strange, because the chip ID register is literally a read-only register that says, this is the BCM5719 hardware revision A1. It's literally read-only. It's burnt into silicon. It should never be reading a 0. Yet there's this code here that is saying, well, if this reads a 0, do this. And then it starts twiddling with these GPIOs on the chip, which are reserved to the ape. And then it's waiting for that register to not read 0. So this is really strange. And I haven't mentioned, this is why it's really nice to have a server board with schematics. So let's take a look at the schematics. I don't know how well you can see, but on the right there, that's our network chip. That's the BCM5719. That's the thing we're trying to reverse engineer. And then on the left, we have this mysterious chip. So you can see that the ape GPIOs that are getting toggled on by this code are on the left here. And then you have some more pins that run into the BCM5719 on the right here. So what are these pins on the right? They are the PCIe reference clock pins. So PCI Express is a differential interface, but it's multi-lane, as you know. So In order to synchronize the clock on all of those lanes, you have a reference clock lane, which has a clock signal, which is then used as a timing signal for all of the other lanes on a PCIe device. So if you install a video card in your PC, you've got all these 16 lanes, but you've also got a reference clock. And you've got these lines running into the BCM5719 Ethernet controller, but ordinarily that would come from the host CPU, and instead it's coming from this weird chip here, which is called a CBTL01023. What is that? It's a differential channel 2-to-1 multiplexer switch for PCI Express Gen 3. Well, that's strange. So we have these GPIOs coming out of the APE, which are controlled by the APE CPU, and going into this multiplexer chip, this analog MUX chip. And then they're coming out of there and going to the reference clock lanes of the same chip. And ordinarily, when the host is operating, you'd expect a reference clock to come from the host and go straight to the device's reference clock pins. And this is all controlled by another GPIO controlled by the APE, GPIO2. So basically, this is an analog MUX chip. It's either connecting these electrically to one input or another, and this is specifically designed to do this for PCIe lanes. So this version register, it should never read 0. If it's reading 0, something is wrong, because it's a hard-coded constant. So if it's reading 0, that means that half the chip isn't even up yet. It's not awake. So this is some kind of code which is trying to fix this and get the rest of the chip to come up. It turned out Broadcom hard-coded the chip so that the non-APE parts only come online after several dozen PCI Express reference clock cycles. Because the host PCI Express interface will always be there, right? Unless you someday want to add this functionality to talk to a BMC when the host is off. Rather than actually fix this problem, they mandated that every customer put an analog PCIe Express MUX chip on their board, so that the APE firmware can manually bitbang clock cycles on the reference clock interface of the same chip to get the rest of it to come up. This is not a joke. This is Broadcom. I'm not kidding. If you have a server with a 5719, and it's still quite common if you, for some reason, order a server with only gigabit Ethernet, it's still shipped there. If you order a server with a BCM5719 and NCSI, your server vendor has been forced to add an extra PCI Express MUX chip to the bill of materials because Broadcom decided to ship this as a design. This is their reference design. So what was the aftermath of this project? I ended up calling the project Ortega. Since all of this is based on reverse engineering proprietary code, I was tainted by the process. From a copyright perspective, this all came from proprietary firmware that I reverse engineered. And there was a desire to produce firmware that had a clean license that we could say this is 100% legal, it is genuinely open source firmware, we hold the copyright, we have licensed this legitimately. Especially since this is shipping in actual commercial products now. So all of the gathered knowledge was used to produce documentation on how to write replacement firmware. You may know this as clean room reverse engineering, and the most famous case of clean room reverse engineering is, of course, when Compaq reverse engineered the BIOS code to the IBM PC so that they could make a clone, and literally every machine, every laptop you use now is thanks to the fact that this clean room reverse engineering technique is actually legal. That's why the PC is a thing. So because I was tainted by the process, I couldn't go and write the replacement firmware. So the replacement open source firmware was brilliantly written by Evan Lajewski, also known as Mechlot on IRC. He couldn't be here today, but he wrote replacement firmware in C++ using the documentation I provided on how to program this chip, all of the registers, etc. And this firmware now ships on all newly ordered Telos 2 and Blackbird Power 9 systems, making these systems finally 100% open source firmware. Mission accomplished. It is also distributed by the Linux vendor Firmware service. you may know it as the firmware update tool. And it's not just for the Telos, right? You can also install it on a BCM5719 PCI Express card for your PC. You can get those on eBay pretty cheaply. So if you just want a PCI Express card that has 100% open source firmware for gigabit Ethernet, you can just buy one of those. Or you can, if you want to tinker with it, for example, and actually play around with all of this firmware. And also, please give a big thanks to Merklort for making open source firmware for the BCM5719 a reality. And as I mentioned earlier, that reverse engineering is kind of an emotional roller coaster. It is really interesting, that aspect of it, because sometimes you think, I'm never going to figure this out, and it just seems hopeless. As I mentioned, the 8, for example, all of the registers for that were unknown. I mean, completely unknown. You had 1 million registers with unknown names, unknown values, and all of the code is unknown. And the thing about reverse engineering is eventually you figure something out. You figure something out, and it lets you figure other things out. And then the discoveries snowball, and it's like this avalanche effect. And then the avalanche ends, and you're stuck again. So there is this constant oscillation in reverse engineering as a field between exhilaration and a sense of impossibility. It's the most exciting thing ever, and then you feel it's completely futile, and again and again. Certainly in my experience, I think that successful reverse engineering requires managing these emotions and persevering. It's weirdly like doing a 100-dimensional crossword with 1 million rows and 1 million columns. I mean, it is like that. You figure out one clue, and it lets you figure out other things. I didn't even consider myself good at reverse engineering before starting this project, which seems a bit ridiculous statement to make now. I just took a quick look at this firmware image to see how inscrutable it was, and it seemed surprisingly scrutable, surprisingly easy to understand at first. And then I got sucked in and suddenly had to decompress the 8, which was much harder. I never could have imagined getting to this point, and honestly, the fact that I managed to pull this off ultimately is really amazing to me. But I have a lot of curiosity, which I definitely think is a really powerful motivator. And I would be really interested to know what motivates others to do reverse engineering, because I think everyone that gets into reverse engineering something like this, that they have their own very personal motivation for it. And finally, please do come and join the community and get involved and ask questions. We have an IRC channel where all of this work was coordinated. The open source firmware is available for you to download and use however you like. You can read the documentation I produced on how to program these devices based on all my reverse engineering, which is how that open source firmware was produced. And you can absolutely get in touch with me and ask any questions about this. And I'd also like to say that now or in years and years' time, if anyone needs to know anything about this device, I'm probably the best equipped person to answer that question outside of Broadcom. So I'm always able to answer questions now or in the future if anyone needs to know something about this chip. Finally, I'd like to thank IBM for open sourcing the Powerline firmware, because honestly, without that, there would have been no point to this. I still think that is an absolutely stunning act. I'd like to thank Timothy Pearson at Rapid Engineering for creating the Telos 2, the system with 99% open source firmware, and providing hardware and resources that helped in this effort. And I'd like to thank Merklort, Evan Ladrewski, for creating the open source replacement firmware, and for the Telos community also for the support and encouragement without which this project could never have been possible. I was ready to give up at various points, and it was absolutely because it was made clear to me how much this mattered to people and how people were relying on me for this, and people really wanted to see this happen. It's why this project was ultimately able to come through and be completed, and why I was able to ultimately achieve success with this and actually complete this project, which certainly is an outcome that is stunning to me. And finally, thank you.
The ups and downs of firmware reversing. Thanks, Hugo, for this talk. Mm-hmm. We are having some time for questions. Line up at the microphone. And there is already a question from the internet, so please.
Yes, correct. There's a question, 2 questions actually from the internet. First one would be, without NIC piggyback mode, one should be safe from the man-in-the-middle attacks from the ape or not?
So the thing to bear in mind here is that the firmware is all loaded from an SPI flash on the main board, and if you control that SPI flash, you're safe, right? So you can audit that, you could attach probes to it if you like and make sure that the firmware on that is good. You can also audit the contents of that flash from the host. There's no way for the firmware on the device to interfere with that, so you can essentially audit this firmware automatically from the host if you want. But if you were to be concerned about what the ape could do, if you don't need that management functionality, there's nothing theoretically stopping you from running without the ape. But obviously, if you're worried that something on the SPI flash could get changed by an attacker, maybe someone with physical access to a machine, they could just reactivate the ape. So that's not a great mitigation. What I would say is that during all of this reverse engineering, I did not find anything that would allow remote exploitation. So while the ape does mem copy data from the network and back and forth, it copies these Ethernet frames, it never truly looks at what is in an Ethernet frame that comes from the network. And the MIPS cores weren't involved in the data path at all. So you don't really need to be worried that there is any exploitable vulnerability in terms of the ape mispassing some frame from the network. It doesn't really look at anything that comes from the network. It just copies it blind into the BMC. Okay?
There's also a second question.
Yeah.
Second question would be, would the new open source firmware allow the implementation of some sort of custom protocol offloaders for VPN, for example? Or is the ape not powerful enough to do this in terms of CPU cycles per second?
It's a Cortex M3. So if you get like a 32-bit microcontroller, that's the sort of core we're dealing with here. So it's not really powerful. As I said, it does this mem copy in order to connect the BMC to the network. And it's not fast. It's far beneath gigabit. So it's not something that you can really do powerful processing with. It's not something that you can really do performant encryption with. One thing that was raised earlier by someone I spoke to was the idea that you could actually forego the use of a BMC and just do some management functions on the ape itself. That is probably possible, so long as they don't need to be computationally intensive. So, I mean, there's some possibility for doing novel things there, but any powerful processing like VPNs, encryption, anything that requires line rate handling of gigabit, forget about it.
All right, thanks. Yeah, microphone number 1, please.
So, as an implementation of the ARM v7m specification, the M3 core should be capable of self-hosted debugging. Did you take advantage of that to run a debug stub on the M3 core and the debug exception?
That is actually a really interesting point. I played around with the NVIC on the Cortex M3 a little, but I did not look at the debugging registers or whether there is any kind of JTAG functionality that might be of use to me, because I didn't really have the hardware set up for playing with JTAG or debugging of that kind. So I never really tried using any of the debug facilities of the Cortex M3. It's all based on shellcode and the tooling I developed that is based purely on software. I don't know whether that functionality is built into the silicon. You could probably find out quite easily, because I believe there's like version registers on ARM cores that tell you whether that silicon is built with that functionality. So you could probably find out pretty quickly if you started wanting to play with the debug tooling to probe some of the registers that we have in the open source firmware. But I don't know.
Okay, thanks. Next one on microphone 1.
Thanks for the talk. I would like to know, do you have any tips or recommendation on provided a proprietary firmware? How did you find out, or I guess a little, the structure of the firmware, like the layout?
So as I said, the first thing I did was just looking at the image dump of the entire flash. So you just do a hex dump and you just start looking at it and seeing what does it look like. Yeah, I run tools like binwalk on the firmware, which just looks for common signs of different CPU instruction sets, and it says, yeah, there's some MIPS code here. It didn't find any ARM code because that was all compressed, but it seemed to match up with what we knew about this device, which was that they had this, this MIPS core and this MIPS firmware. And there were other parts that were pretty obvious where you run binwalk and it says, oh, there's this x86 code. And you look at that area of the code in just a hex editor, and it's pretty obviously a PXE option ROM. And you just start getting an understanding of what the different areas of flash do. And as I said, it doesn't take that long in order to get to a place where you get the image layout. So if you look at so yeah, you've got the image layout here. And a lot of it is just eyeballing, really, where you see little strings there, here and there, or you see the device MAC address there, and it becomes pretty obvious what the different regions do. It is like doing a crossword, and you do sort of get better with experience, but it's basically just finding something that seems to make sense, and then that helps you find other things. I hope that helps.
Okay, thanks. Microphone 1 is very, very popular, so just go ahead.
Thanks for the talk. So tying back to an earlier question on offloading stuff to the hardware. Mm-hmm. So now that we control the firmware on the ape, do we gain more access to more features that aren't actually available to the driver?
So in terms of using the peripherals, if you can think of some useful thing to put on the ape that uses those same peripherals, you can probably do it. But because this ape was designed to implement a feature that Broadcom specifically wanted, namely NCSI, you're not going to find much functionality there that is helpful hardware-wise to do things that aren't required by that feature. It is pretty targeted. But if you wanted to do like some novel management feature that reuses the same peripherals, in principle, you could do that. But the peripherals are pretty specific to what you would need to implement NCSI.
Mm-hmm. Thanks.
Yeah, and the next one.
Right, so you mentioned there was a cryptographic signature, but it wasn't checked.
Yes.
Would there now be the possibility of, and would there be a point in creating signed firmware with a custom key and insert that key into the bootloader?
So what's going on there is that the bootloader is a mask ROM. It's hard-coded into silicon, and it happens not to check that. So not really, because we can't change the mask ROM, right? That is Broadcom silicon, which is just hard-coded to load an image in this way. If you wanted to get more control over the firmware image and make sure that it hasn't been changed, I think the best way to do that would be to write some program to audit the firmware from the host. Because as I said, the host has the ability to reflash the firmware, and that's all hardware registers, so the firmware can't actually interfere with that process. So if you wanted, you can just read out the firmware image from the host and get an accurate reading of what is on that flash. That would allow you to audit what is going on there.
All right, thanks.
And one last question from the internet.
Yeah, the internet wants to know whether you also checked or compared your findings with other Broadcom network interface cards.
I haven't. I know that things have changed a lot with the faster network interface controllers, like the Net Extreme 2, which does 10G and above. I am certain that those are actually enforcing signature checks now. So I do not believe that this work would be viable for those. That seems to be very much the standard for the network interface controllers for 10G and faster. If they've got some kind of firmware, they're doing some kind of signature check on that. I believe Broadcom does that. I believe Intel does that. And it's not really hard to check. If you just look at like their one-page marketing brief for a chip, and they say it has secure boot, you can pretty much guess that it's probably checking signatures in the hardware. The other thing I would say is that, yeah, I mean, the 10G chips are very different. I suspect that Broadcom has stopped using the Tigon IP that descends from this chip that began in 1997 with Alcyon networks. I'm not sure that they took that forward with the 10 gigabit parts. I think they may have finally scrapped all of that legacy here. But for this 1 gigabit chip, which is basically the chip Broadcom will send you if you're looking for a 1 gigabit chip for a server, this is the last remaining descendant, I believe, of the Tigon line.
Okay, thank you everybody for your questions. Thank you, Hugo. Hugo, for your talk.
Thank you.
Please.